Folks, I want to welcome you to the third installment of our tech tips discussion. And this one is going to be covering issues around hose selection and troubleshooting. And if you're doing anything in that world, you probably have had a fair amount of trouble in your own mind and your own life trying to get this right. Doug Nordstrom, who I'll get into a little bit of his CV in a minute, will be leading this discussion, and I think you're going to find it very enlightening, informative, and also, Doug, you may want to talk about at some point some of the new things that are going on in your operation right now in terms of new technologies and test procedures. So with that, just a little bit of housekeeping. First of all, Cody Hildebrand, Denver Swagelok field engineer, and Brian Bullard, who's our training leader at Swagelok Denver, are going to be joining us here, and they're going to be available to answer any questions if they come up, as will Doug. If you look at the bottom of your panel on the screen, you'll see a Q&A option. You'll also see a chat option. Use either one, whatever is your preference, to communicate with us, and we will answer them as they come up. Secondly, we've got a couple polls we're going to push out here, so we'd like you folks to participate and give us your unblemished truth in terms of answering this, because we're learning as we go along. And last but not least, a message from the corporation. We are the Swagelok Denver Service Center. We service most of Colorado and Wyoming, exempting the southwest portions of each state. If you're out of our area, we can't support you. You will find, however, a sales and service center in your area that is going to be capable, more than capable, of supplying you with any kind of products and services that you might need from Swagelok. So with that having been said, I'm going to introduce Doug. Doug Nordstrom is a decorated veteran of the fluid system wars, 25 years at Swagelok. If it has happened, he has probably seen it. He has 14 years as a product manager, covering things from regulators and valves to probably any other thing you can imagine. And the last 3 years, Doug has been the senior hose product manager and is bringing some fascinating new capabilities to our hose world. So having said that, Doug, I'm going to turn it over to you and take it away.
All right, thank you, Charles. Yeah, that was very nice. And thank you, everyone, for joining. Today, we're going to be talking about basically some things we've learned in the hose world in my 3 years of working with the hose products at Swagelok. We're going to start off relatively simple. We're going to talk about some background on hoses, just to make sure we're all on the same page. And then we want to get into the two biggest issues we see with hoses when we get hose issues at users' sites. And then we want to get into some unique things that are done to create hoses. We call these hose construction efforts, basically. And those are going to revolve around permeation and also metal hose. So with that, we're going to get started on a background of different hose types. Like Charles said, please feel free to ask questions at any time. We'll take some stops and try to answer them as we go on. But again, we want to start off relatively simple and go through what makes up a hose. A hose is different than a tube in that it's multi-layered. A lot of people think hoses are flexible and tube is not. Well, that's not the case because you have flexible tubing. The difference is flexible tubing is one layer, where a hose is multiple layers. And the inner layer is a core tube, and that's where we want to start. That's what sees the actual media. So that's what we need to be concerned about when it comes to contamination or compatibility with whatever's flowing through the hose. But the actual core tube is actually many times very, very thin, less than a millimeter, less than 40 thousandths of an inch thick. It withstands at the most 50 to 100 PSI, just a couple bar of pressure if you use bar. So for that reason, the core tube needs to be reinforced. It needs to be stronger, and this is typically done with a braid material. and the braid can either be done with a fiber braid, which is what you see in the black in this diagram, or it can be done with a metal or stainless steel, which is pretty typical, which is the gray braid, or both, which is what this hose is. That raises the pressure of the hose from, again, 50 psi or so to thousands of psi, whatever it might be, depending on how strong the braid is. The braid keeps the hose from growing in length under pressure and growing in diameter under pressure. And then many times this braid is covered. The cover is typically done for a couple reasons. One is the braid is very difficult to clean. So if the hose needs to be cleaned, the cover needs to be put on so the hose can be washed down. But also the braid material can fray a little bit and become a little bit dangerous. It can be pokey. And so the cover material is there to protect the braid, protect people from being injured by the braid. And then obviously every hose has two end connections, and these end connections are put on in different ways. The one you see here is put on with what we call a crimp, where the barb is inserted into the hose and it is then squeezed, and that's what we call a crimp. But there's different ways to put on different end connections. The four main types of hose that we're going to talk about are listed here. The top one is a metal core, and so this is a little different than what we showed on the previous slide. This hose actually has a metal inside, which is extremely thin, and we can't crimp a metal hose, so what is done is it's welded to the end connection. This is full metal all the way through, and the metal core is corrugated in order to make it flexible. If you imagine a very, very thin tube without corrugations, it would kink and bend and break very quickly. So the corrugations are put in to make it flexible. The next one down is what I showed on the previous slide. It's a fluoropolymer or PTFE or Teflon core hose. These are very common because of their chemical compatibility. And in this example, this hose is crimped on. So the outside sleeve is squeezed to the end connection and makes a strong enough connection so that the end connection doesn't separate under pressure. Thermoplastic hose, they were basically developed to withstand pumping pressures, hydraulics, pressure spikes. They're very forgiving with a lot of pressure impulses, and they're typically made of a lot of soft materials. And then lastly is rubber. A rubber hose is very rugged, down and dirty, general industrial type product. The end connections are typically just pushed on, very easy to make. And again, very, very rugged type product. Now these are important to understand because every hose performs different given different system parameters. And we see this all the time where a very high quality hose is put in the wrong application, and that hose will fail very, very quickly, even though it's a very high quality hose, just because it's being applied to the wrong type of system parameters. And this is intended to be basically a cheat sheet or a quick reference guide as to what type of hose is good for what type of parameters. So what we're saying here is metal core, for example, is very good in temperature. Thermoplastic, for example, is not. It is a low temperature material. It will fail very quickly at higher temperatures. So if we take a high quality thermoplastic hose and put it in a high temperature application, it will not perform well. At the same time, if we take a high quality metal core hose and put it in a pressure impulse, where pressures are spiking very quickly, application, it will fail very quickly, even though it's a very high quality hose. If you think about metal, like a paper clip, if you bend a paper clip back and forth, it will fail relatively quickly. That's what happens with the metal core hose. So it's important to understand the system parameters when selecting a hose. And what we've seen is this isn't always done. A lot of users of our hoses simply put the hose that was in place previously back in place, and it might be the wrong type of hose for that application. So it's always important to really evaluate what the hose is going to see through its lifetime in the application before you choose what type of hose to put in the application. And we understand this isn't always easy. For example, if you have a high temperature and pressure impulse situation, what's the best hose? And it's not always the easiest thing to select the right hose for the situation. And for that reason, Swagelok has what we call hose advisors that can go and give recommendations based on what the hose is going to see in the particular installation. Some different examples of this, and again, we've seen a lot of this through our time. One is this particular picture you see on the right, where this tire press moves up and down about 6 feet, and the hoses in this case are moving up and down about 6 feet with that U shape. And the particular hose that was being applied was failing in about a few weeks, about a month. And it was because it was the wrong hose for this high temperature steam application. So we were able to look at this situation, understand the dynamics of what the tire press was doing, suggest a different hose, and we've now had these hoses in service for about 2 years, and they're still going strong. So even though the hose was more expensive than the rubber hose that was being applied, obviously it's a cheaper installation because it's lasting far more than 50% longer. So it's a better situation. It's safer, and everyone wins because of a better hose application. Another situation we see very often is hoses that don't have a preventative maintenance program. And this is very important, and this is one of our first poll questions, by the way, Charles. No one goes out and buys a car and doesn't plan on doing maintenance on the tires. Everyone has a preventative maintenance program on the tires, and they're in their head, ready to do, rotations and service on the tires because they all know it's a service item, it's a wear item. And that's what a hose is in a fluid system. It's the wear item. A lot of times fittings and tubing, they're not wear items. They're going to last a very, very long time, if not forever, where a hose will not. And we're very surprised how rarely preventative maintenance programs exist for hoses. They will always wear out. They're a wear item for a fluid system. And just helping a user of our hoses establish a preventative maintenance program so they can plan for the right downtime, they can plan for the hose to be replaced at the correct time, saves it a huge amount of money. In this case, it was over $500,000 for this particular customer. And that's very common. So I always ask people that use hoses, how often do you have a preventative maintenance program? Are they on all the hoses in your system? Do you even know where all your hoses are? And are you planning for the correct downtime so that you can replace them when it's not a costly time or a safe time to have those hoses out of the system?
All right, Doug, should we let them have have a shot at the poll here?
Yeah, sure.
Okay, here we go. Let's take a quick look at this and give us your answers and see what you think about it. Basic question of, do you even have a preventive maintenance plan for your hose situation? I'm going to give it a couple more seconds, but it looks like the leader in the clubhouse is we don't have one. We replace hoses when they fail, followed closely by don't know. So I think it sort of proves your point, Doug.
Yeah, that's very common. That's what we've seen, and it's something to keep in mind because hoses, of course, are a big safety item. So so not knowing when they're going to fail obviously can be a concern financially and safety wise.
All right. Let's press on, sir.
We'll do. How do I get back to it, Charles? Close that. Okay. Okay, so building off that safety issue, not only are hoses a wear item that need to be planned for maintenance, but they're also a very commonly handled component of a fluid system, up there with valve handles and things like that. But because of this, because they're touched very commonly, disconnected and connected and moved around due to their flexibility, we need to make sure that we take into account the people, the operators that are going to be touching the hoses. And we see injuries because of touching hoses very, very commonly. Things like braid wires that I was mentioning before can scratch and cut skin. Hoses can be worn away and they're therefore damaged and can be dangerous. But in this case, this particular hose, we call this a steam tattoo. But basically what happened is it was a steam line and it was at 200 C or 400 degrees F. And this individual just rubbed up against it and obviously left a pretty significant burn. This is something that's relatively common. So for this reason, hoses should always be considered for different accessories. What we show on the right is insulation to make the outside of the hose safe to touch, but there's things like abrasion material that stop braid wires from abrading away, and different outside accessories that make hoses safe to touch and handle. These things are always, it's always important to consider these when selecting the right hose for the application. So with that, we're going to move now into the proper installation. So the idea is you want to consider everything going into the application when you select the hose, and now we want to make sure you install the hose correctly. And we see a lot of issues when it comes to proper installation. The picture on the top right is a perfect example. That hose obviously has been damaged due to the installation. It was bent incorrectly, and it's been kinked in 2 different spots, and that's always damaging a hose, and we don't always consider that. The hose on the top right obviously is too short for making that bend, and there's some significant damage there at the end connection. In the bottom in the middle, that hose was routed across a tow motor path and was run over, and clearly damaged. And these are many times afterthoughts and not really considered an issue, and I'm not really sure why. It's always a safety concern. These hoses have been damaged and can be obviously ruptured and cause an issue. The most common is what we call kinking, and I think we all know what kinking is. We all go out and take our garden hose and bend it and make the flow shut off, and we all think it's funny. But in an industrial application, it can be very, very serious. What kinking a hose is doing is bending it beyond its minimum bend radius, and what that means is it's bending it beyond its elastic limit. So it now has permanent damage, and what that's shown there on the bottom right. This hose has been bent to the point where it now has permanently been damaged at those oval spots, and it no longer will withstand the same pressure rating it did when it was originally built. And too many times people think they can go out and bend it back into shape, massage it a little bit, it looks like it's round, and it's going to act like it was when it was brand new. And this isn't the case. For those of you that are engineers out there, we know that when something is plastically deformed, it is now no longer to its original state. No matter if it looks like it is or not, it's permanently damaged. And this can be a bit of a concern because you can't tell when a hose has been kinked because you can make it look like it wasn't kinked. So it's always very important to let a hose be routed and move in a way that it will not kink. It can be a failure point for a hose.
Hey, Doug.
Yep.
A couple folks have asked some questions here. You want to take them on right
Sure
now?
thing. Yeah, absolutely.
All right. Adam asks, hopefully you folks can hear me well. How do you recommend tracking hose usage and or deciding when to replace and retire a hose? Probably the $24 question.
Yeah, that's a very common question we get. Unfortunately, it's not very easy. Every hose application is different due to the dynamics that the hose might see, due to pressures, whatever fluid is flowing through it. And so we get the question very commonly to help establish a lifetime of a hose. And the short answer is we can't really do that. We understand how long hoses last, and what we've also seen, we understand how long hoses last in a particular lab application. In a actual customer application, we don't. That's maybe a better way to describe it. But what we do know is that hoses last a very consistent amount of time given the same application. And that's a good thing, because if you start to establish the hose life in an application, it will most likely last about the same amount of time the next time, the same hose. So our best suggestion is we need to establish that data for each application on its own. And that's not always easy, right? Because it requires failures, but it's always the best way to get that data.
Okay, and a second question, how do you properly implement a preventive maintenance program in your facility?
So what we have done is the first step obviously is to start cataloging the hoses. Where the hoses, give it a name, put a tag on it, start tracking that in an Excel sheet or whatever form you would like, and mark the install date, and start documenting things that the hose will see on a regular basis. How often is it cycled? How often does it move? How often is it used? And you track the install date and the failure date. And that's the best way to start getting that data. But the first key in all that is cataloging. Yeah, every hose has to have a name, and every hose needs to be down on a sheet so that you know when it was born and when it died.
All right, care and feeding of hoses. Okay, we're all good. I think that answered it. If anybody has any further questions on that subject, just type them into the Q&A box and we'll get to them. Back to you, Doug.
Okay, great. This is a very common kink point we see. What you see here in the picture, where a hose is bent right at the end connection. This is a very dangerous thing to do for a hose, because where the hose is crimped, as you see in that end connection, it is being stressed to a great deal. And this stress will make that kink fail. We always strive, and we're very proud to do so, where our hose end connection actually doesn't fail. It's always, when we overpressurize and burst a hose, the actual hose bursts, not the end connection. The end connection does not fail. However, doing something like you see in this picture can cause the end connection to separate, and that's a very dangerous failure mode, because it's a large burst. It's a lot of flow. It's a lot of hose whipping around, and it can be very dangerous. So we always say, make sure the hose has enough length so that it can be straight when it comes out of the end connection for 2 ODs, two outside diameters. It's a much safer way to route a hose. This is something that relates to the dynamics of a hose. Obviously, hoses are always, not always, but many times dynamic applications. And because of this, there were some industry standards that were established on determining the right length of a hose in different dynamic movements. These aren't Swagelok defined equations. These are industry equations, and we train on them. Our field engineers, our hose advisors all know them. But they help determine the right length of a hose. And this is very common that we see these not followed. So for example, on the tire press, where the tire press is moving up and down 6 feet, if the hose fails in a month, like what we were seeing, many times it's because the hose wasn't the right length and it kinks very quickly at the end connection. When we go in and use these equations and determine the right length, the hose will last much longer because it's not being damaged by the kinking that happens when the hose isn't the right length. And so too often we see a hose fail and the user orders the same hose to the same length and puts it back in service, and of course it fails again. So always understand, especially in a dynamic application, that the hose length is critical in determining what the hose lifetime will be. Very common failure bending at the end connection is just the lack of elbows. We see this on our own shop floor, unfortunately. When I walk around our manufacturing facilities at Swagelok, I see hoses routed like this all the time, and it drives me nuts. But a simple elbow here would make this hose last far longer. The weight of the hose pulls down consistently 24 hours a day, 7 days a week, to the point where it's going to fail at the end connection. And then if this is liquid, inside of the hose, that additional weight will continue to pull down and will make the hose kink at the end, where a simple elbow would solve this problem very, very quickly. Very, very common routing issue. And then lastly, in dynamic applications especially, what we see is bending in two planes. And what this means is, can you take the hose and put it down flat on a table? And the picture on the right, you can't. The hose is coming out vertical and going into a horizontal plane that's moving back and forth. You can imagine that hose can't lie down flat on a table because it's bent, what we call, in two planes. What happens in this case is the end connection moving back and forth puts incredible torque on the hose. And twisting or torquing a hose is a very, very fast failure. It's a very easy way to kill a hose. And simply routing a tube, or in this case a static hose like you see on the picture on the left, makes the hose now bend in one plane. This hose will last hundreds of times longer than the hose on the right. Bending a hose in two planes, torquing a hose like what you see, is a very, very fast death, and the hose on the left will last hundreds of times longer. So with that, we're going to move to the second most common issue we see, other than poor routing, which is what we call static dissipation. This is something that we see in Teflon or softer core materials. So this is a PTFE Teflon core hose, and what you see in these pictures is the braid removed from the outside, the metal braid removed, and it's a burn mark. What happens is the Teflon actually collects electrons from the media that's flowing through the hose on the inner wall, and these electrons build up. It's very similar to rubbing your socks on the carpet in the winter and then reaching for a light switch. What happens when you reach for a light switch is you get a shock because the electrons that you build up inside your body and need to jump to the closest conductive thing, which is the light switch. Same thing happens in a hose. The electrons need to jump to the closest conductive material, which is the braid on the outside. When that happens, a spark shoots through the Teflon core, creating a pinhole leak. And the hose then obviously is failing, and the hose has different pinhole leaks throughout it. So this creates leaky hoses. There's different things that cause this to happen. Most notably is what is flowing through the hose. Different medias create these electron deposits more than others. And we have a list of what creates this, and a lot of them are a lot of different hydrocarbons, which are very common in general industrial hoses. Also steam. Steam is a very common media in hoses. These things create electron deposits on the inside of Teflon hoses. The second issue is flow rate. the faster the media flows, similar to shuffling your feet faster on the carpet in the winter, the more electrons will deposit. We've seen many applications where this wasn't an issue, and someone goes and turns up a flow meter, a rotometer, or whatever, and all of a sudden, all the hoses start springing leaks. So just the flow rate through the hose causes this. And then other things, of course, like humidity, temperature, everything you would expect from understanding static buildup. So this is very easy to fix, and we don't see it fixed very often, though, and that's the issue. So we always want to understand whether or not static dissipation is required in a hose. First of all, the best way to fix it is use a metal hose, because a metal core hose will dissipate static instantly. It's going to flow the static charge right through the metal core very, very quickly. But if a PTFE hose is needed, the best way to do this is with a carbon core, and this is a common product for all hose offerings, and it turns like you see in the picture on the right, it turns the core into a black Teflon because of the carbon. And the carbon's infused into the Teflon. It won't leach out. It's not a coating. It's built into the Teflon, but it's enough carbon that allows the electron buildup to flow out of the hose safely without creating a spark. It's very easy to do, and it's very common, but people don't use it as often as they really should. In some cases, customers are interested in whether or not the hose is conductive. So what we're trying to do with this slide here, with these pictures, is show that static dissipation and conductivity are two very different things. The hose on the left is a nylon braided PTFE core, so there's no metal, and it has a carbon core. So we applied a voltage across the hose and measured the resistance, measured the current and resistance. And what we had here with this hose is 80 million ohms of resistance, 80 mega ohms. That's a huge resistance. There's very, very low current, but it's enough current to dissipate the static buildup, and that's what's important. So this hose on the left is considered to be static dissipative, but is not conductive. It's not going to act, for example, as a grounding wire from one end connection to the other. It's not conducting electricity in the level that you would think. The hose on the right is a metal core hose. So core, metal braid, metal end connections. It's metal through and through. And doing the similar test, this particular hose had 0.4 ohms. So instead of 80 mega ohms, it has 0.4. So this is 200 million times less resistance. This hose does act like a grounding wire. This hose is conductive. It also dissipates static, but it's also a conductive hose. It conducts electricity. Now, if you take the hose on the left and you don't have it be carbon core, it essentially has infinite resistance, and that's what we're trying to avoid in order to be able to dissipate static. So the key here is, if you have a media that is going to build up static charge, like or different hydrocarbons, make sure that your hose is a carbon core, a carbon-filled core, or it's a metal hose for that matter. Otherwise, it's gonna create a static charge and have a leak very, very quickly. This is a very common issue we see, and it's very easy to fix. If you're concerned about conductivity, a carbon core does not make a hose conductive. It's got a 80 million ohms of resistance. It's not conductive. So, and again, always reach out to Swagelok hose advisors if you have questions on this. But we can offer a product that solves this issue. Okay, moving on to permeation. And now we get into a couple different things that revolve around how a hose is built, how a hose is created, that can impact the way it performs in particular applications. And the first one, again, is permeation. And just to make sure we're all on the same page, what permeation is the flow of gas molecules through a solid material. And so in this case, it's flow of gas molecules through the hose core. So a PTFE Teflon core, for example, will have gas molecules flow through it. And that's what the permeation is. I mean, quite simply, it's the reason a balloon doesn't stay blown up very long. It's because the air inside of it permeates out of it. It's not because there's a leak. I mean, permeation is a leak, I suppose, but it's not because there's a hole. This can be a safety concern, and this can also be a financial concern. Whatever's flowing through the hose maybe is an expensive gas. And so gas permeating out of the hose can be expensive. And maybe more importantly, if the gas permeating out of the hose is in a confined area that's not ventilated, it can become explosive if the gas is explosive, or it can become an asphyxiation issue where there's not enough oxygen left in the room. So permeation can become a major issue in some cases, and in other cases it might not be a big deal. So that's the first takeaway, is understand whether or not permeation is an issue for a hose application. We've done a lot of studying on permeation, a lot of testing, and we understand this actually very well. We understand that the surface area of a hose is directly linear to the permeation rate, which makes perfect sense, right? If you have a hose that's twice as long as another, it will permeate twice as much. We also know that pressure is directly linear. So if a hose is at 1,000 psi, it will permeate half as much exactly as a hose that's at 2,000 psi. We also know temperature is linear, except we have to keep in mind that temperature is related to absolute temperature. So of course, 0 degrees Celsius is 273 degrees Kelvin. So going from 50 Celsius is like going 273 to 323. It's not as big of an impact. It's related to absolute. And then wall thickness of the core tube makes an impact. The thicker the wall, the less permeation. But the last one on this item here on this list is what we're learning the most about, and that's what we're calling the sintering method. This is a process of creating the Teflon core of a Teflon hose. When Teflon is originally made, it's extruded basically into a tube, and in its purest form, it has a lot of holes in the Teflon molecule creation. Sintering is a way of baking the Teflon that tightens up the bonds and makes the holes smaller. So this shows an example of what we're talking about. If we take just a raw Teflon non-sintered 1/4 inch hose, pressurize it to 3,000 psi of nitrogen, it's going to permeate about 150 cc's, 150 milliliters for 1 foot of hose in an hour. So that's actually quite a bit of gas loss, right? It's almost a liter of gas in about 8 hours. If we take that same core and we do a process called slow sintering, which takes the core and puts it in a pizza oven. If you imagine a pizza oven that flows, put the pizza on one side and it moves through, and when it comes out the other side, it's baked. If we put that core tube into a pizza oven and slow sinter it, it drops the permeation rate of the same hose to 20 cc's per foot per hour. So about a 7.5 times improvement. If we take that same core and we do what's called a post-sintering method, which is more costly, takes more time, but it puts the entire core into an oven and similar to baking a cake. That same core tube drops to 4 cc's per foot per hour. So that 150 cc's of gas loss, nitrogen loss, drops to 4, about almost 40 times improvement, which is obviously very substantial. This shows basically the same numbers, just graphically. And so what we want to stress here is when you use a PTFE Teflon core hose in a gas application, it's critical to understand first of all, how important permeation is, eliminating permeation could be, and secondly, how the hose is made. Is the hose going to perform well in this application? And there's a wide range, and too many times people look at a PTFE hose and they think they're all the same, and there's a huge range of performance that you could see.
Doug, should we have another go at the poll number 2?
Yeah, perfect.
Here we go. So what types of hoses do you use when permeation is a concern? And be honest, gang. Okay, give it a couple more seconds, but again, it looks like we've got a lot of don't knows on this issue, and sounds like this information could be pretty valuable going forward, Doug.
But yeah, that's fantastic, of course. And again, we're always here to help.
Okay, we'll end the poll there. Here are the results.
Okay, great.
And pressing on, sir.
All right, that brings us to our last topic, which is understanding the way metal hoses are made. And I brought this up at the beginning, but a metal hose is very similar to a paper clip. If you bend a paper clip enough, eventually it will break. Metal hoses will wear out from bending, similar to a paper clip. But depending on how it's made, they can perform very differently. So to get this started, we have to understand how a metal core hose is first of all is made, and it starts with a very thin strip of stainless steel, about 0.008 of an inch thick, which is about 2 pieces of paper, and it's rolled into a tube and seam welded. So every metal core hose has a seam weld, and then in order to have it be flexible, it needs to be corrugated. You can take that picture in the middle, and you can imagine if you try to bend it, it's going to kink and break very quickly. But once it's corrugated, it now becomes very flexible. And this corrugation process is really the key. How are these corrugations put into the hose? The most common way is what we call a mechanical forming process, where rollers move around the outside of the hose. Then these rollers are in the shape of the corrugation. And as the rollers move around the outside of the hose, they press into the hose, stretching the material and forming the corrugation shape. You probably know that this pressing method is going to work harden the material, and work hardening metal makes it fail faster. And the rolling process is going to put a twist into the hose. And that's what you see in the middle picture here. The seam weld, you can see, I hope, in the picture, is twisted around the outside of the hose. And I mentioned before with bending in 2 planes, twisting a hose, torquing a hose is a very, very fast death for a hose. And what will happen with these mechanical formed metal hoses is, in a dynamic situation where the hose is moving back and forth all day, every day, it will end up breaking very quickly at the root of these corrugations. And that's what the picture on the right is. The roots of these hoses will crack and break and create leaks very quickly because of the work hardening and twisting that the hose is seeing. An alternative to this is what we call hydroforming or crimp forming. And what these hoses do is they are pressurized on the inside with thousands of PSI of water. And again, the actual core tube of a hose only withstands 50 to 100 PSI. So this hose wants to burst, but is being pressurized inside of a die, inside of a mold. that is in the shape of the corrugations. And when this happens, the hose stretches into the corrugation form, and that's how the corrugations are created. Obviously, everywhere on the inside of this hose is pressurized the same, so there's very, very little work hardening. There's some stretching of material, but the work hardening is very, very much minimized, and the actual twisting in a hydroformed or crimp formed hose is completely eliminated. There is no twisting at all. The downside, of course, is it's slower. It's not as fast to produce. So uh, it's a much longer lasting hose in a dynamic application, but it costs more to do. So there's always a give and take, I suppose. So both types of hoses have their value. It's just which hose is being applied to which application. And again, similar to PTFE, not all hoses are made the same. Not all metal hoses are made the same. In a dynamic application where a metal hose is required due to temperature or whatever it might be, it's important to understand that the hose should be hydroformed or crimp formed. A mechanical formed hose will fail very quickly. In a static application, mechanical formed hose might be better because it's lower price. So again, it's important to understand the application, which type of metal hose is being applied, and for the most part, a dynamic hydroformed hose will last up to 10 times as long as a mechanical rolled metal hose. And with that, I think we're out of time, and we also are out of material. So basically, it's important to understand, what type of hose you're using for your application. Swagelok is here to always help. We have our hose advisors, we have our field engineers, and we have a lot of different hose products that we can help make sure we have the right one for your application.
Super.
Charles, do we have any other questions?
Yeah, I got several here. The first one is the carbon core food grade? The hose with the carbon core, is that food grade hose?
It is, actually. It's a question we get very, very often. We've done a lot of testing, and we have FDA approval on our carbon core. A lot of people shy away from using it in those applications because of the black. It looks dirty, but it's not. We've done all the testing, and it does not shed out or leach out, whatever word. So it is FDA approved.
Great. Cody, you had a couple questions there that you came across?
Yeah. So, Doug, if you subject an all-metal hose to gas pressure impulses, does it perform better than if you subject it to liquid pressure impulses?
Yeah, good question. Liquid is the worst. Similar to what you might know in your own plumbing, like water hammer. Liquid impulses can be very, very dangerous on a metal hose. So gas is more, obviously, is compressible. So the gas impulses will have less of an impact, but it's still not the best for metal hose.
Do you know which Swagelok PTFE core hose was used in the dynamic steam application?
Yes, it was our T series. Our T series hose was used for that particular application because it's post-sintered. So the permeation was a bit of a concern for our customer, and the post-sintering obviously limits the permeation the most, and so that's what they wanted to go with.
In the presentation, you'd mentioned that all metal hoses connect kind of like a grounding wire. Are there applications that you know of when you need a hose to act like a grounding wire?
Yeah, that's a tough one for me. There's different situations, and they're kind of random, where a particular piece of equipment is grounded and another one isn't. And so it might be a bit broad, but the hose will ground that second piece of equipment. Now, the applications are very broad, random a bit, depending on the electrical hookup of the different equipment. But the actual metal hose does constitute as a grounding wire.
Does that apply mostly to applications with like gasoline or diesel fuel or things that conduct electricity very well and also will probably be subject to higher flow rates?
I would imagine, yes, although I might not be the best to answer that question, but yeah, I would imagine that's the case.
Okay, we got a couple other questions from the other participants. We can get a copy of this slide deck to share, right?
Yeah, Cody and Charles, I have it posted. You guys can send it out. You're more than welcome to.
All right, well, everybody that's both on this and that couldn't make it will get a link to see the deck and the recording. That'll be sitting on the Swagelok Denver YouTube channel as well as our website. So, and if you want just a hard copy of the slides, we can get you those too, just ask.
Okay, and then another question was, are Swagelok PTFE hoses post-centered? And I would guess that the attendee wants to know if all of the PTFE core hoses are post-centered.
So what our hoses are, our T-series hose is post-centered. The rest of our PTFE hoses are all slow-centered. So they're not all the same because they come at a cost. So we felt it was appropriate to have one that was post-centered, essentially the top performing, and the rest we felt were okay being slow-centered.
And I think there's a last question about Swagelok metal hoses, and are they all hydroformed, or do we also, much like in the sintering, give you a set of options?
We have options because we know that it's not always worth the additional cost. All of our hoses are hydroformed except our FM. So when you look at our catalog, our FM is mechanically formed.
Great.
So it's a better hose for a static application.
So they can come to us for pretty much any need they have in that regard, I guess.
That's right. That's the idea.
Right.
One more question is, does permeation occur only when the gross flow axially through the hose is really low or not at all?
So permeation is related to pressure. Pressure and flow aren't necessarily connected. So if the flow in a hose is high or low, it still will permeate depending on the pressure inside the hose. Does that answer the question?
Yes, I believe so. Because,
okay.
For example, if you're using a hose downstream of a regulator, the pressure is going to be a lot lower, so the permeation rate is going to be a lot lower than if you used a hose upstream of a regulator.
Right, right.
All right, that looks like about it on the question front. Just to reiterate, folks, there will be a link coming your way, which will connect you to this recording and all the slides. So feel free to share that. If you do want just a hard copy of the slides and don't want all the back and forth we've had, though why you wouldn't want that, I don't know, but we can get you a copy of the slide deck also. Last call for any questions? All right, looks like we're there, Doug. I want to thank you so much for your time and your information. It's been great.
Yeah, my pleasure. Thank you, everybody.
All right, guys. See you later. Next time.
Thanks all. Bye.
Bye.